The first thing I want to do, though, is introduce you to an Australian tradition. This picture is of my hometown, Canberra, the capital of Australia, and it's Ngunnawal country. It was first settled about 80,000 years ago, continuously occupied, used, and improved by Ngunnawal people, and then in the relatively recent past, invaded without any kind of legal grounding. I live just off to the left of this picture. I was born just off to the right, and I work in the middle. It's a beautiful place, and I want to pay my respects to the elders of the Ngunnawal people, past and present, who care for it, and for the leaders emerging. It's a talk in 4 parts. I'm going to talk through what I think of as the state of the art of testing, with my background working on PyTest and Hypothesis and working on a PhD in this area. I'm going to talk you through the internals of Hypothesis, how it's implemented, how it works, and I believe why it works. A couple of extra techniques that I think of as indistinguishable from magic. They're almost science fiction because they're really cool techniques that very few people have implemented because they seem somehow harder. And then I'm going to finish with a call to action. That is a concrete demonstration of what you can do with these tools tomorrow, and finishing with a live demo. I have never tried a live demo over the internet before, so it will be a learning experience for all of us. So let's start with the state of the art. How do I define testing? Well, for me, testing is any way to check whether your code is correct, which involves actually executing your code. This actually rules out very many very useful techniques. It rules out linters like Flake8. It rules out type checkers like MyPy. It rules out all kinds of formal verification that we could do. But the advantage of testing is that it's relatively easy to check sophisticated invariants because you don't need to learn any new techniques. You just write a Python program. And if the program, that is the test function, raises an exception, your test has failed and you presume that your code is broken. There's a couple of different ways of testing, including auto manual testing, where you write out the full test case, but there's also a number of techniques that actually allow the computer to assist you. So let's talk through those. The first question is why you would want to use these more advanced techniques for testing. And I think this is the core reason, that no matter how rigorously you analyze your code or how imaginative you get, you can never write test cases for bugs that you don't know about. So fundamentally, we need to be doing something different than just writing out what we expect to happen in known happy path cases if we want to discover new bugs through testing. So tests, which I call auto manual, where we both write the full test, specify all the values for it, and then specify exactly what we expect the outcome to be, they simply don't scale either. Humans are relatively expensive. Certainly, my time costs a lot more than CPU time. But don't get me wrong, I think there is always a place for this kind of test, and they're particularly good for checking tricky edge cases or to make sure regressions don't come back into your code base. So what could we do that doesn't require us to imagine all of the test cases we might want to try out? Well, the first and simplest example is exhaustive testing. We just execute every possible behavior of the code or every possible input to some function and check that they're all correct. Obviously, this is great if we can do it, but as soon as we're dealing with non-trivial data types, there's just too many. So if you have a 32-bit integer, you can check all possible integers. If you have 2 of them, 64 bits is just too big an address space to search exhaustively. And so we only have time usually to specify some of the behaviors. The other problem is just that checking whether the behavior is correct for some given input can often be quite difficult. So we need to analyze this in terms of higher properties, that addition might be commutative, that a plus b equals b plus a, and we don't actually need to know what the correct sum of those integers are to check that property. Of course, this even gets harder when our requirements are from humans or are for business logic, and then they can change over time. But more on that later. On the other hand, exhaustive testing can sometimes be really useful. This is a simple test case I put together for NumPy because I've had some trouble with Unicode arrays in the past. We simply create an array that holds one string of a single character, and then we iterate over every Unicode character except the null character because the strings are null terminated, and we check that we can put the string into the array and then access it and get it back out. And I got a Unicode decode error. But what made this really interesting was that the error message you see there is not actually what was happening. The character that this failed on was not a surrogate character and was not in that byte range. As of the most recent release of NumPy, this has been fixed, it turned out that a complicated interaction between their Python 2 and Python 3 Unicode compatibility layer had a small error in it. Very simple test, but I hope I've convinced you that this is already a valuable trick. Another great technique is to take a corpus of existing tests. This is really common for protocols if you're implementing a standard protocol, or if you're dealing with something like JSON schemas. There's a third-party test suite which consists of a list of inputs and the expected output for each. Whenever you can find one of these, I would strongly encourage you to use them. If you randomly sample from them, sometimes they can be a bit flaky, but the corpuses are usually small enough that you can just exhaustively sample from them. And this slide takes 3 examples from the big list of naughty strings that you can find on GitHub at that link. I think my favorite thing about this slide is I actually tried to add a 4th string, one which had a bit of Hebrew text in the middle. So the text went right to left, then left to right, and then back to right to left. When I did that, PowerPoint crashed. So how else might we find crashes? The simplest way would be to think of a single function. The most general kind of function we might think of is one which takes a string of bytes or a string of bits and does something and maybe returns a value, but we'll ignore the return value. Conveniently, most programs at a high enough level look like they basically take some bytes of input and do something and maybe produce some output. And this gives us a really simple way to test them. We simply pipe the output from dev random or another string of random characters into our program, and if it crashes, we found a bug. This technique was memorably described in a paper on the reliability of Unix utilities from 1989. The paper begins, "It was a dark and stormy night. One of the authors had logged into his workstation on a dial-up line from home when it was raining, and so there was frequent noise on the line, and it became a race to see if you could type a successful command before the workstation crashed." Of course, the line noise on dial-up in the rain in the 1980s was not surprising, but the fact that this would crash the computer instead of giving you wrong results was surprising. It seemed reasonable to suggest that programs should always give you some kind of error message instead of crashing when something goes wrong, at least if that's on bad input. This was a common technique in the era of punched cards as well. You would get a deck of punched cards and shuffle them and feed them back through your program. If it crashed, you had some work to do still. To make this applicable to more complex programs, instead of just generating random inputs, because very few random strings are, for example, valid HTTP requests or valid JPEG images, we can start to look at coverage. So coverage tools fundamentally ask, what part of my code was executed? You can talk about coverage in a number of resolutions. You can have which of the functions in this file were executed, or which lines were executed, or which possible branches, which flow control graphs were executed. And so this lets us identify the smallest unexecuted unit, which is a very valuable thing for test suites. You can tell if you're missing tests because some parts of your code were not executed by your tests. That means you know that your tests couldn't find bugs in the unexecuted lines. But looking at coverage lets us pull off an even cooler trick. This one's called fuzzing. If completely random generated inputs are unlikely to be valid, instead of generating random inputs, we can start with valid inputs and make random changes to them. Maybe we take the first half of one and the second half of another, or we take a prefix of one and generate some random bytes, or we try flipping bits or corrupting bytes. And this doesn't seem too useful until we combine the idea with coverage. If we combine coverage with random mutations, what we can do is slowly evolve a population of inputs which cover, that is, execute more and more functions or lines of code. So initially, almost all of our inputs might be rejected quickly. But when we happen to randomly find one which makes it a little further through our code, then we'll notice that from our coverage. And we can start spending more of our time mutating that input, trying variations on it. And this is a powerful enough technique, it turns out, that within a few minutes you can go from absolutely no knowledge of any input file format to generating valid JPEG images or valid PNG images. So we are evolving inputs that cause our code to crash. This is even more powerful in compiled languages where you can add sanitizers, such as a memory sanitizer or address san or undefined behavior sanitizer. so that your code crashes on a wider variety of kinds of bugs. In Python, we tend to have to do that using assertions. So I put a lot of assertions in my code as well as my tests, so that if something happens, I get an input that I don't think should be possible, or I get a result that indicates that there's a bug elsewhere in my program. That becomes a crash rather than an incorrect return value. So, second part of the talk, let's look at how hypothesis works. Hypothesis is a tool for what's called property-based testing. Instead of writing tests where you give an exact input value, run some calculation, and assert that you got the expected output value, you write a test which should pass for any valid input value. That's the property. So for example, the property of addition that we might be testing is that it's commutative, that a plus b equals b plus a. Or for a sorting function, we might assert that running the sorting function on its output does not change it. The function is idempotent. And so while assertions in code are great, we can describe restricted inputs and thus make even stronger assertions on our tests. I'll talk more about the properties that we can test when I get to the live demo. So the final part of property-based testing is how do you describe the inputs? In hypothesis, we simply have what we call strategies. So you might have the integer strategy, which can generate any possible integer, or optionally you can give it a minimum and a maximum value. Or we have the float strategy, or we have date times, or we have a strategy we call builds. You can pass it your class plus strategies for the arguments to that class, and it will give you instances. So these are implemented in a variety of ways internally that we generally keep private because they can change at any time. Collections are implemented as a strategy which takes another strategy. So if you want lists, you can say you want lists of integers, and I'll show you that in a few minutes. We have a number of cool tricks which make this perform better than should be naively possible, basically because we cheat. And then what we do internally with that is we basically turn our property-based test into a fuzz target. So we treat the strategies as if they describe a parser, and then we have a fuzzer which generates some bytes. We use our strategies to turn the bytes into values, and then we run your test function. That also means that we can conveniently save any previous failures, which is really useful because it fixes the problem where random tests may or may not fail the next time you run them. If you run a hypothesis test and it fails, and you run it again, it will always fail again unless you've fixed the bug. And the final really useful trick that this lets us do is generate a minimal counterexample. We don't just generate any kind of failure when a hypothesis test fails, but a minimal one. So integers close to 0, lists with the fewest elements possible, and in this case, a demonstration of how a tree might shrink. We have our byte string or our bit string, which represents the tree, and we try a number of operations. So this first operation is just to take the first subtree. The second operation is, again, to chop off part of the subtree by replacing it with a single node. And then our last simplifying operation is to switch the order of the subtree. So this is our minimal example of an unbalanced binary tree, which we found after generating a much more complicated example. And I know that whenever I'm debugging something, I always prefer minimal reproducing examples. Of course, it's not guaranteed that we're going to find the truly globally minimal example. Essentially, we're operating like a compiler with a number of parsers. We guarantee that the example we have is sufficiently minimal that no operation that hypothesis knows how to do will find a smaller one, but it is possible that there's a smaller example that we don't know how to find. These operations correspond to things like deleting regions of bytes, switching sections of them around, and because we have the strategies, the parsers that describe your data, we can be much more intelligent about how we attempt to do this. So that's a real gain in efficiency. And then part 3, some techniques that go on top of property-based testing that add some more power. These are, I think, approximately magical in how effective they are, but also notable in that, to my knowledge, hypothesis is the only tool that implements these outside of the research papers that originally proposed them. So the first is called swarm testing. This is a really neat technique in that you don't actually need any feedback or information about how the code works or what the strategies are in order to run it. all it does is it generates more failures with the same number of test cases. And there's a pretty simple intuition for that. Instead of generating random data, we first generate a random distribution of data and then generate random data from that distribution. This might make more sense if we consider the idea of a stack that can overflow. Let's say we have a total of 25 operations, and in order to fail, we need to push 20 things onto the stack in a row with no pop operations. So if at each step we randomly generate a push or a pop, we're very unlikely to get a run of 20 pushes in a row. But if we start by randomly generating a mixture of pushes and pops, we've got about a 1/3 chance of generating only pushes. And as soon as we do that, we'll find the bug immediately. So I tend to find this is just a fantastic optimization. In the worst case, it's roughly harmless, but in the best and expected cases, it makes our testing way more powerful. Targeted property-based testing is essentially giving you the power of coverage-guided testing without needing the overhead of measuring coverage information. So this is really useful for example, numerical code. If you have some kind of error budget or an imprecision, you can tell Hypothesis to target that, and it will preferentially try variations on examples that had relatively high scores. We have found that this evolves to maximize the score quite effectively. It can do multi-objective optimization. People have even used it to test C code by using the coverage from C code and generating their inputs with Hypothesis. The catch is that if you pick a metric that doesn't correspond to bugs, we can evolve to preference that and so actually decrease the chance of discovering bugs because we've evolved in whatever direction we were told to. So, very powerful in principle. We do support this in Hypothesis, but it is sometimes risky. Most of my tests don't use targeted property-based testing. The final one that I've been working on lately is constructing programs. Instead of just generating things like lists or integers or strings, trying to generate, for example, Python source code. That is syntactically valid Python source code. This was something of a challenge, but I thought actually very useful as well because there are a wide variety of tools that operate on Python source code. We have the formatter black, we have the AST module, we have type checkers, we have linters, and all of these tools should handle any string which is valid Python source code. And so I thought to myself, well, if I can get Hypothesis to generate Python source code, maybe I can find bugs in them. I have found a lot of bugs in them. Very few tools handle comments with a carriage return in the middle, for example, but no new line. The grammar is kind of tricky around how we deal with white space. And I have taken this a fair way. So if you are writing tools which operate on Python source code, try using Hypothesis Smith. I'll show you a link to that later as well. What I'd love to do next, and I would love to find contributors to help me with this, is go from generating syntactically valid source code to semantically valid source code, stuff that it's actually legal to execute. That would let us test not just linters and formatters, but also interpreters to make sure that all our different versions of Python or different implementations always get the same result from running any given program. All right, and now onto our call to action, where I talk you through what I think you can do with Hypothesis tomorrow. The simple one, of course, is just write property-based tests. They are easier, they are more powerful, and they find bugs that I would never even think were possible without them. Step one, of course, is to install Hypothesis. That one's pretty easy. You just pip install Hypothesis or conda install Hypothesis. Hypothesis is released very frequently. We average a new version every few days, and every pull request is automatically released as a new version. So if you contribute a bug fix or a new feature to Hypothesis, you never have to wait more than about half an hour for that to be available. Once you've installed Hypothesis, step two is to migrate an existing unit test. So in this example, I'm going to walk you through testing something like a Git integration. So we have a repository and we have a branch, and our test is that checking out a new branch makes that the active branch. So our traditional test is here. We create a temporary directory, we initialize a new repository, we check out the branch new branch, creating it, and then we assert that that's the active branch. So the first step is just to go, what parts of this could we move to default arguments? This really helps us semantically to distinguish between what's essential features of the test and parts of the test that should pass for any value. So essentially, we're just saying this should be true for any value of branch name, that if we check out a branch with that name, then that name is the active branch. To use hypothesis, instead of setting it as a default argument, we can use the just strategy. The just strategy will only ever generate the value it's given. So these three changes haven't actually made any semantic change to our test yet. We're just getting ready for property-based testing. The step after this is usually to pull that strategy out to a custom function or maybe a global constant. And so we're still only returning the name new branch, but we're saying that this should pass for anything which is a valid branch name. I hope this makes sense. I can't see the audience reaction for a change. And so our next step might be to say, well, what's a valid branch name? Is it any Unicode string? And if you read the Get manual, it turns out that no, most strings are in fact not valid branch names. You can't have the empty string, you can't have strings starting or ending with white space, and there's a bunch of other rules. So we're going to restrict this a little more. We're going to say, give me any string of text which consists only of ASCII letters that's not the empty string, so min size of 1, and that's at most 95 characters long. That's because some web services impose a 100-character limit on the branch name, and the branch name in that sense includes head slash. Once we've done that, we can come back to the test body, and we're going to upgrade this. So eventually, we can take this to generating not just new repositories, freshly initialized ones, but given any repository in any state. If we have generated a branch name that is not already the name of a branch, and then we create it and check it out, then that branch name is the currently active branch name. So incrementally, we've moved from a traditional unit test to extract what our argument should be, to generalize what our argument should be, and then eventually to generalize the whole test to a property-based test. All right, and now for a live demo. This part is actually going to show off a new capability which is not yet released in Hypothesis because it's still under review. It's the Hypothesis Ghostwriter, because lots of people have told me that they're not quite sure what tests to write. So the aim of the Ghostwriter is to actually help you write your tests. You can give it a number of different properties, a fuzz test, which simply executes your code many times with different inputs and sees as it crashes. A round trip test, that's something like reading and then writing your data gets you the same data back. Idempotent, that calling your function on its output makes no further changes. Or an oracle test that checks that two functions are equivalent. So let's start by running this one. So a fuzz test for re.compile might look something like this. We have test fuzz compile. It takes an argument for the regular expression pattern and one for the flags. It tries to compile that regular expression, and on an error, it just tells Hypothesis that that was a bad input and it should try something else. If we run this immediately, we discover that something is going wrong. There we are. When we run this, we discover that we can't actually generate any information because we're using the nothing strategy. It's special in that it can't generate anything, so it's a good placeholder, but we actually need to generate patterns. So let's replace this with the text strategy that says any Unicode string should be a valid input here. And then if we run our tests again, we'll see that our tests pass. This is good that the standard library regular expression module can do that. If we want to see what inputs Hypothesis is trying, we can do that, and we need to disable output capturing. And we have a whole range of different patterns, some of them long, some of them short, all of them things that I probably wouldn't have thought to put in this test. So let's try another ghost written test. Next, I'm going to suggest that we look through the oracle test. So we're going to compare the ast.literalEval module with the actual eval built in. So what might be a valid string? Let's just try text again. Should any string work for this? Well, what we see pretty quickly is that, in fact, not every string is a valid input to ast.literalEval. In this case, when we try to eval the empty string, we get an unexpected end of file, which I guess is fair enough. Ultimately, it turns out that the only valid inputs to literal eval, that is, turn the string representation of a Python literal into the actual objects, is of course things which are valid representations. So let's try lists of integers. And then we're going to convert those lists of integers into the representation of them using the repr built in. So we take any list of integers, call repr on it, and that will be our node or string. And if we run this, the test should pass. Except it turns out that our ghostwriter has supplied keyword arguments here where eval only takes positional arguments. So let's try that again. All right, that time it passed. Let's check what inputs it was using. And this is various strings representing lists of integers. So far, hopefully, so good. All right. Next test, we're going to go through all 4 of these together. We're going to test that the sorted function is idempotent. That is, that it doesn't modify its own output if we run it again. So what shall our iterables be? Let's try lists again, and we'll do lists of text because I'm kind of sick of integers. And if we run this one, yep. We're going to try a whole bunch of different things. And it turns out that this fails. Why on earth does it fail? Sorted got 0 arguments. All right, so the minimal example that we end up getting is that if we passed reverse equals true to the first one, then we actually also need to pass it here. And so now that we've fixed our test case, I think this should pass now. We're asserting that if we sort this, then it passes. So what I'm hoping that I've shown off to you is the way that I end up co-developing my test suite with my actual code, that you can incrementally adapt the tests that you're writing. You don't have to get it all right up front. And you can actually learn a lot about how the code works through property-based testing. Last demo, because this one is the most complex of them all. We're going to test that if you take any valid JSON object and then you turn it into a string and you turn it back into a JSON object, you get an equal object again. So this one's going to be quite exciting. Not least because JSON turns out to take way more arguments than I knew about. So we're just going to delete a whole bunch of these. We're not going to deal with encodings or any of that stuff. Let's see. That goes. So we now have a simpler thing, and let's go JSON strategy. What's the simplest JSON value? I think it's going to be just null. If this passes for null, then hopefully it will pass for some more complicated things. All right, have I gotten this right? Let's find out. Got to delete that argument. All right, so our test passes. This is good news to me. Our test passes at least if the only thing we generate is none. But of course, there are many other possible JSON values. For a start, we could have none, we could have a Boolean, we could have some kind of floating point value, or we could have some text that is a Unicode string. All of these are valid JSON scalars. So let's try running our tests again and see what happens. And pretty quickly, let me run that again. Pretty quickly, we discovered that one of the float values we've just said are allowed is nan. That is not a number. And, sorry, we've generated inf. In fact, we've generated infinity, whereas we've said that we should not allow that in our JSON encoder. So let's specify that we'll not generate allow nan here. We're just going to default to always allowing infinite values. And if we do that, then our test still fails. Live coding over the internet. Our test still fails because not a number is unequal to itself. So while it round trips, it doesn't quite work. That's simple enough to fix though. We can simply write an assume statement that our object equals itself. So that'll fix it. That will exclude not a number, and then our test should pass. And it does. So the last thing we want to do is be able to generate more complex JSON. Because JSON is recursive, we're going to use the recursive strategy. And JSON is either a scalar or it's going to be lists of some JSON or dictionaries of string keys, that is text, to arbitrary JSON values. And at this point, we're going to see something fairly interesting. We're going to learn something about how Python's equality semantics work. Something that I genuinely didn't know until I started writing this test. What we found is that a list of not a number compares equal to itself at this stage, but then not equal to itself once it's round trip through JSON. When I dug into this, it turns out that as a performance enhancement, Python list equality first checks the identity of each element in the list. So the 0th element of this list is by identity the same in each. And because they're the same list, it doesn't proceed any further with comparison. So that is the bulk of the live demo. You can see a simpler form there for if it didn't work. And I would now be delighted to take any questions from the audience.
It was a very nice presentation. Very interesting to see the ghostwriter. We will now transform our discussion to a questions session. So I'll just wait until that happens. Да, мы сейчас переходим к сессии вопросов и ответов. И у вас должны быть специальные ссылочки в Zoom уже, я надеюсь, с заготовленными вопросами, чтобы мы смогли на них дать ему ответы вместе с Заком. Я напоминаю, что вам нужно там при переключении, когда вас будут включать, чтобы вы будете задавать вопрос, вам нужно останавливать звук из трансляции, иначе из-за вот этого лага с трансляцией Zoom у вас может возникнуть слишком сильная обратная связь и будет все слишком сильно фонить. Вот, поэтому обращайте на это внимание. Не забывайте включать камеру, не забывайте, да, что включать микрофон тоже нужно, иначе вас не услышат. Вот, ну и как бы не стесняйтесь, не бывает неправильных вопросов. Мне кажется, что Зак вполне может ответить на практически любой вопрос про тесты и про применение озвученного фреймворка. Вот, так. Чтобы мы смогли на них дать ему ответ вместе с Заком. Что? Я напоминаю, что вам нужно там при переключении, когда вы... Я слышу снова себя. Да, ну вот, сейчас у нас первый доклад, первый опыт подобного переключения, поэтому мы ждем ваших вопросов с нетерпением, так сказать. Да, у нас появился первый вопрос. Привет. Вопрос задает Паша Финкельштейн. Я думаю, Паша сможет спросить его по-английски вполне. Так. Да, Паша, у тебя включен звук, говори, пожалуйста. Да, так. Паша, надо проверить, что у него включен микрофон. Окей.
Hi, Zach. Thank you for your talk. I have one small question, quick question, I think. So basically, we can get flaky test because one time our test can fail, and another time our test cannot fail if it's a random test, property-based test. So is there any way to easily reproduce tests?
Yes, so there are several ways. The first is that we also have an @example decorator. So you can literally just write out the failing example at the top of your test function, and it will be replayed every time. The second way is built in. If you're rerunning your test locally, they will never be flaky, because the first thing we try is we replay all of the previously failed tests. If you're reproducing something from CI, we also print the random seed that we used, as well as a decorator with a compressed version of the test case. So you can slap that on, it will then replay, it will fail, and that will be added to your local database as well. So while we generate inputs randomly, we aim to never have flaky tests. That's a core part of the design of Hypothesis.
It's a little bit complicated. Okay, thank you. So how should it work on CI? I think that it makes sense to run property tests on CI, but it won't be able to save, previously failed tests.
Most CI services allow you to cache some directory. Often that's for installed packages, but you can add the Hypothesis example directory to that list to persist between caches. When you're reproducing things locally, we just recommend having the setting in CI that then also prints the example that failed in a format that can be reproduced locally. Our documentation has a whole page on how to reproduce examples, which I would recommend reading.
Okay, thank you very much.
Окей, да, спасибо. Если есть какие-то еще вопросы, не забывайте поднимать руку, чтобы технический модератор мог вас обнаружить и, соответственно, передать вопрос. Okay, so I see there are no more questions at the moment. My question is regarding tests. I have a recent experience with adding tests to a system that had a lot of interactions with other parts. Like we had a database with a serialized protobuf in that, and then we had to test our custom class with a compiled protobuf serialization, deserialization routine and test some of the processes there. And I ended up writing a lot of mocks for the parts that were not available on the system, but I was wondering if Hypothesis can help me with, I don't know, writing the first of all, if it can help with writing mocks properly in the places where it can just see that something is not installed. And the second is if there are any ways to like fast testing like a byte string of something that needs to be deserialized and serialized in a particular fashion.
The second part first.
Okay.
The simple answer is yes. One of the strategies is for byte strings. You just say, give me binary strings. You can tell it a length or of any length, and it will generate random byte strings for you. Another trick, if you're dealing mostly in protobufs, is there are some third-party extensions to hypothesis that take your protobuf class and generate arbitrary instances which could be serialized as protobufs. So you could generate your protobuf instance, turn it into a byte string, and then maybe flip some random bits if you wanted to test maybe malformed protobufs. But when it comes to mocking specifically and how you do integration testing, I kind of think that's orthogonal to the design of hypothesis. So you might want to use mocks, or you might want to use it for integration tests, but hypothesis is more about how do you deal with the inputs to your test rather than what is it that you're testing.
Okay, I see. I think I'll have one other question. Do you see any other like? I think I heard about a few others similar frameworks currently being developed. Like I think there was one called Behave, but it's mostly outdated right now. That had some sort of hypothesis testing built in, and is that anyhow superior to hypothesis, or is it like far behind? Are there any other alternatives for this type of packages?
Sure. So there are many alternatives in other languages. So the most famous is QuickCheck and Haskell. Haskell has a lot of them. People really enjoy writing this kind of framework. In Rust, there's PropTest. For C and C++, there's the deep state library from Trail of Bits. But in Python, as far as I know, there is basically no competition at all. I would say that Hypothesis is one of the best property-based testing libraries for any language. And okay, I might be biased as a core developer, but I'm also doing a PhD on the topic.
Yeah.
Most of the other libraries that I know of are simply random generation. So there's Faker or Fake Factory or Factory Boy. They just have lists of possible inputs that they randomly select from. And so you have the problem of flakiness, and you don't get minimal examples either.
Okay, cool. I think we have one other question from Pasha again. So, yep, speak.
From Alexander, okay, but let me ask first, it's in Zac, how should we, can we extend, like text generation? Can we say that we need only text according to some regex pattern, for example, like generex or
one of my
like
favorite strategies is called from regex. You hand it a regular expression, and it gives you strings that match the regular expression.
Oh, okay, thanks.
We also have some extension strategies, so you can use any context-free grammar.
Okay, I think we have one other question from another participant. Alexander.
Oh, yeah. Yeah, can you hear me? Nice. So thank you, Zac. I really appreciate your kind of talk. Maybe I will switch the topic slightly out of the details, but I see you have a lot of experience in that. And actually, when we're talking about testing in general, I mean, as the industry, maybe as the process, right? Maybe you can somehow highlight things that were most important for last maybe 5 years. What things are dramatically changed from your point of view? What we maybe stopped doing, what we're going to do? I guess this is quite interesting.
I agree. So I think the biggest change for industry, maybe the last 20 years, was just that unit testing has gone from something that a few people did to something that almost everyone does. And I think we're in the early stages of seeing computer-generated tests making that same transition. In about 2000, unit testing was kind of rare. It was popular with extreme programming and with the agile programming crowd, but that was still a rare thing. And now property-based testing, I think, is in a similar place. It was on the cutting edge, but it's now moved out of academia into industry. And while there's only relatively few people using it as yet, it's getting more popular all the time. And so even just in the last 2 years, maybe 5 or 10 times as many people are using Hypothesis. And there are similar tools popping up for almost every other language that you could think of. So I think it's that integration where we go, how can we automate more of the testing? How can we use more advanced tools? And how can we automatically enforce more and more properties of our code?
So I guess I have a follow-up question. So you said that the current hypothesis state is like it's still evolving. It's quite stable, but it has a lot of feature plans.
Yep.
So what do you think? Like what's the timeline of the current like a backlog? Like how far in the future you have a feature plan for something that you want to implement in this?
Well, the short answer is actually we don't have any development plans. We don't have a roadmap. We have an issue tracker which lists a number of features that we would like. The Hypothesis is developed entirely by volunteers in our spare time.
Yeah.
Some of us are students, others are professionals working on other things. So the timeline is more or less features happen when somebody comes along who is willing to write the code for them.
Okay.
So if there's anything that the audience wants to see in Hypothesis, you are welcome to write it and we will merge it and it will be released 20 minutes later.
Is there anything like in particular that you're just waiting for someone to implement and you think is quite a nice sort of first level contribution to Hypothesis that you can like, you just don't have time to do it, but you would love to have it, that you can just name on top of your head?
Yeah. Hypothesis is mature enough now that we have very few of those issues left. So the most valuable thing is actually to start using it on other projects.
Okay.
For example, NumPy, Pandas, SciPy, AstroPy, all of them have decided that they will use Hypothesis, but currently have very few tests that use Hypothesis. So working with us to write tests for other projects is probably the best way to help the property-based testing ecosystem.
Okay, so basically the user base must grow, and that's what drive the development.
The user base must grow, and other projects need to adopt Hypothesis.
Okay, cool. I think we have one other question from Vladislav. And yes, no?
Yeah, can you hear me?
Yes.
Yeah, thank you for your talk. So I have a question. Yeah, could we use Hypothesis for generating of different pandas data frames, and what's about performance of Hypothesis in this case?
Certainly. We actually ship Pandas support with Hypothesis. For optional dependencies, we have hypothesis.extra, and for pandas, we have hypothesis.extra.pandas. So you can say what rows you want or what columns you want, what indices you want, and it will generate random data frames for you. Performance of Hypothesis tends to be quite good. Typically, tests will take somewhere between 5 and 20% of their runtime generating data, and the rest actually executing the test function. Obviously, this depends on what kind of data you generate. If you generate very large data frames or array, you do very small operations, then it will take longer to generate. But performance is usually quite good. If you have performance problems, you can use the statistics option, and it will give you much more information about which parts are slow, so you can focus on speeding up the hotspots.
All right, I think that's most of the questions that people are ready to ask straight away. I remind that we have a discussion zone, so please follow up there, and I'll just...
Hello, everyone.
So guys, we are finally connected. So I also want to stress out that we're just kind of testing the new format. So I guess we're ready for the discussion. So I guess we can do an experiment here. Maybe we can turn on all microphone that we have right now, and we just can do kind of rambling around different topics. So let me maybe just start and make sure that Zac also, I mean, your background, right? Something which is kind of your background is quite nice. I guess you tried all these things with the toilet paper, right? I mean, during this last few weeks. So by the way, talking about this stuff, are you working right now from home?
I am. My entire university is working from home. Everyone who is not doing lab work related to virus vaccines is working from home. Staff, students, teachers, everyone.
That's a huge boost, I guess, for all these technologies. I mean, so I think this is a nice thing, to be honest.
Yes, we've all been learning how to use Zoom, that's for sure.
That's true. So let me ask our moderator to help me and connect more people, because I see a lot of kind of muted microphones. Just a sec. So, by the way, maybe you can tell us a little bit more about kind of maybe your thoughts about the future of testing in general, because I heard a lot of kind of controversial things, like people can stop testing and all. I mean, in general, like not only using tools kind of and using unit testing, in general, like we will find something which will totally, let's say, get rid of testing as the idea. What do you think? Is it a utopia? Is it a real thing in the near future? Maybe, I don't know, in a few years or thousands of years. What do you think?
Yeah, it's kind of been the dream for decades, right? Everybody wants to write code that just works the first time. The problem is, it turns out it's a lot harder to write code that does exactly what we want it to than it is to write code that does almost exactly what we want it to. I know that I've never written a significant piece of code and gotten it exactly right on the first try. The question of whether testing is the best way to check that our code is correct, I think broadly does remain open. The main advantage of testing is that it's really easy to start writing tests. The disadvantage is it's hard to be completely certain that a thing works just because it's tested. Sometimes people argue that we need formal proofs, for example, that code does what it's meant to. The catch there is that it tends to take a little longer to develop the formal proofs than it does to just write a few tests. So my view is that the correctness of code, whether it does what we intend it to do, is actually almost a question of economics. We know that there are a wide variety of ways that we can try to get code that is more and more certain to do the right thing. But the more certain you want to be, the more it costs to develop that code. And so what makes me excited about tools like Hypothesis and some of the emerging tools like auto formatters, like type checkers such as MyPy for Python, is that they give us a broader range of places that we can be on that spectrum. We can just run a type checker and not write any tests, and that tends to be quicker and cheaper, but more likely to leave bugs in. Or we can write a few tests using Hypothesis, which might even be faster than writing a lot of traditional tests. Or we can write a lot of tests using tools like Hypothesis, which takes just as long, but it makes us much more confident that our code works. Or we can go all the way up and use a tool like Crosshair, which tries to exhaustively calculate every possible input, symbolically execute the code, and prove that there are no bugs in it.
Yeah, that totally makes sense. And you know, also, I want to point on this topic. I guess it's also quite an international thing when, you know, I remember that story that people kind of start, a lot of people, they start their career in testing, maybe in QA or doing kind of some manual tests. Yeah. And right now I see that all these practices that we discussed, I mean, these practices actually moved this tradition slightly away. I mean, more and more people understanding, I mean, right now, I guess most of the people understanding the real reason of testing and the impact, right? And what do you think? Is it a right movement to do kind of testing across different departments and roles, or we still need to grow more people who will do just, for example, manual testing, or they will practice in something which is called UAT or user acceptance testing? What do you think? Is it a good idea?
I think it really depends on the industry to a large extent. Often when I'm thinking about how do we test and how do we decide what to test, I look at hardware manufacturers like Intel, because just like writing software, writing chip designs, it's possible to have logic errors or other problems. But unlike software, it's a lot more expensive to push a patch, where that means remanufacturing 100 million CPUs. And so hardware design companies tend to invest much more heavily in testing, and it generally makes sense for them to spend a lot more time and effort on testing. So in many companies that design hardware, a tester can be just as much of an expert as a high-level software engineer. Teams will be a mixture of developers and testers. And importantly, I think testing is seen as a skilled occupation. It's something that requires not just effort, but expertise, advanced tooling in the same way that we would have IDEs or compilers, and requires people to work really closely together. So I think in some ways we're likely to see a continuation of the trend where some people will be expected to be full stack. So you write your back-end code, your front-end code, your tests for everything all in one job. But I think we'll also continue to see places where having people with particular expertise in even sub-areas of testing will still be a valuable thing.
Yeah, and I'm totally agree with you, because from also my experience and from my point of view, I mean, absolutely the same picture that I see right now. And, be honest, I mean, I've also joined the industry, I don't know, more than 10 years ago. And one of the most important things for me at that time was kind of to find the tool to make an automation for testing. That's actually what my real path, how I start the career in kind of mostly in programming and managing people in development. But I mean, I guess if you guys, I mean, still have somebody who do kind of testing, this is a good candidate who can do a lot of different stuff. And typically all these people, they finally grow into PMs, I mean, and a lot of different kind of product roles, because the understanding of things, I mean, what's behind this, I mean, it's really important. Also, I want to touch one more thing. So I guess most of us, I mean, familiar with the standard or, I don't know, language, DSL, it doesn't matter how to name this. It's called Gherkin, or so mostly it's kind of for this nice notation. And I guess it was a revolution that time. I mean, when people somehow explored this thing, and then the popularity and the kind of this thing actually start very, very kind of growing rapidly, right? And I have some feelings that today we are waiting for maybe something really new. I mean, something that will change the industry one more time. What do you think? Maybe you have some ideas or maybe examples of tools or maybe some kind of technological radar, right? I mean, that we need to take into account.
I mean, there's an old saying, I'm not sure if it's in Russia as well, but it goes, predicting is hard, especially predicting the future. So the short answer is, I don't know. I think there are a couple of candidates, things which could be big and could change a lot of how we work. But a fundamental part of it is that testing is actually really hard, because you have to understand what the code is supposed to do. And when you find a bug, you also have to understand what the code is really doing in order to fix it. So I think most of the advances are going to be in the area of tooling rather than in understanding. So through till maybe 2000, 2005, we regularly saw languages that had new ideas. We saw procedural, functional, object-oriented languages. I don't know that we've seen a new paradigm in language design lately. Rust is particularly interesting to me because I think the main selling point of Rust is just that, not that Rust invents new things, but that Rust has really good engineering behind ideas that we already know of. So the idea of the borrow checker, of memory safety have been around for a long time, but Rust is the first language that does them really well and matches that with really good performance. In terms of testing, I think there's a couple of options. One is we get much better at things like random fuzzing or generative fuzzing, where a computer can, independent of any human, start searching for errors in our code. The advance for that, I guess, would be automatically writing tests, not just finding crashes, but finding incorrect behavior. So in a small way, the Ghostwriter prototype that I have is kind of aiming to do that for you. You can declare a property that your code should uphold, and it will then write a test that can find counterexamples. Obviously, that works best if there are type annotations so that you don't have to supply your own strategies as well. Beyond that, though, there's some really cool stuff in formal verification where the tooling just keeps getting better. So there's a tool for Python called Crosshair, where you can write a docstring which lists your pre and post conditions, and without actually executing your code, it will turn it into a Boolean satisfiability constraint problem, hand that off to an analytical solver, and try to synthesize counterexamples for you. The problem is that most of these techniques are relatively fragile. So they work really well in some cases, but the places where they work tend to be cases where we don't really need them much because the code is already fairly simple. The biggest one that I think we're actually starting to see is probably formal verifications for design rather than for code. Because if you only specify your system at a level of abstract actions, you can generally write a fairly short spec, maybe a few tens or up to a few hundred lines of code, and quickly find very subtle design issues. So this is not when your code does the wrong thing, but where your design is not consistent with what you wanted. So your database can lose data if some sequence of actions is taken, or you can have a message delivered twice under certain constraints. These are problems that you could in principle find by testing, but it's far, far cheaper and more efficient if you can find them before you write the code, when you're still working on the design of the system.
Yeah, absolutely. I mean, you mentioned that fortune teller is kind of quite hard job, right? I mean, but sometimes kind of doing a proper testing and development, it's more like also predicting the future, the understanding the status of your release. So that's cool. And maybe we can somehow wrap up this nice talk. I mean, and you know, I mean, typically I'm trying to ask some stupid maybe questions, but I don't know. By the way, why in Australia a gas station, let's say named server? What's the idea? Why is that? Why is that true? And if it's server, it's not a gas station or a supermarket. What's the story? Maybe you know. I mean, I asked a lot of my friends, and they all of them they struggled. I mean, to describe the reason.
Australians tend to be quite lazy with our use of language. So if a word is long, we tend to shorten it. And if we've shortened it too much, we add O on the end. So servo for a fuel station is short for service station, which we then shorten to servo. Similarly, a bottle shop becomes a bottle-o. On the other hand, if a name is already short, we tend to lengthen it. I can't explain that at all.
Yeah, so I guess this is a good explanation about kind of the way of kind of doing the things shorter and kind of trying to find the nice kind of naming for different things. I guess we're very, very close to each other about kind of using this technique. So that's cool, and I guess we're good enough. So thank you guys. So let's move on. Thank you so much, Zac. That was
thank you very much.
Yeah, thank you.
I'm delighted to have spoken to you, and I look forward, hopefully, to seeing some of you in Moscow in September.
See you.
So long.